In this unit, we'll talk about the derivative applied. That is to say, applications of the derivative. Now, historically, this is actually where the calculus began, with applications of the derivative and the integral, which we'll study later, to all sorts of very practical problems in the physical sciences. It was only later that the foundations were developed that we have been learning about up to this point. So now we actually get down to the business of seeing where calculus is most useful. And the very first thing we're going to look at is graphs of functions. And first thing we'll look at is analyzing the graphs of functions, and there are many things to learn. So we'll start with analyzing the graphs of functions 1. The first thing we will look at is increasing and decreasing functions, the first derivative applied. First, before we can look at what calculus can tell us about increasing and decreasing functions, we want to find out what increasing and decreasing functions are, just to remind ourselves. So let's break this up into two parts and do it for the increasing first. The easiest way to see it is to imagine that here is a picture of an increasing function. Now, we want to write down what that means specifically. What it means is if you have an x1 and an x2 on the x-axis and you go from left to right, and one way to say that is to let x1 be less than x2, then ask yourself what happens to the f values, the y values. Well, here I have f of x1, and here at this height I have f of x2. And notice that f of x2 is bigger vertically than f of x1. That is the defining property of an increasing function. So what we'll say here is that f is increasing, and I'll just write down what we saw visually here. It's very hard to get this wrong if you draw a picture. F is increasing means that x1 less than x2, this situation here on the horizontal axis, implies that f of x1 is also less than f of x2. And that's what we saw on the y-axis here. So the inequality is the same in both of them. If we look, however, at a decreasing function, something like this, and we try the same analysis, here's x1, here's x2, x1 is less than x2, we move from left to right. Here is the height of f of x1 now, and here is the height of f of x2. We see that f of x1 is the bigger one this time. So if we want to write this down, we see f is decreasing. And what does that mean? That means if x1 less than x2, which is what's happening on the horizontal axis, if that implies that the relationship now is that f of x1 is not less than but greater than f of x2. So this is switched directions. Some students try to remember this by thinking one of these has a switched direction, but that's really the wrong way to go about this. The best way to go about this is to remember the pictures. You can't get it wrong if you look at these two pictures. So keep that in mind, and that is the definition of decreasing. And of course, we assume that this happens on an entire interval for both of these, so we can say a function is increasing on an interval or decreasing on an interval. And just to put on the bottom here, what would happen under the conditions that f was a constant function? Well, that would mean that if x1 is less than x2, or x1 is just not equal to x2, then that implies everywhere in the interval in question that f of x1 is equal to f of x2. It is constant. It never changes no matter what the x1 and x2 are. So here's our basic definition of decreasing, increasing, and constant. And now we're going to see how the calculus can help us find those things out. So what we want to do here is we want to connect f being increasing or decreasing to f prime, its derivative. And it all comes from a very simple observation. If you have an increasing function like this one, we see that f here is an increasing function. If you examine the slopes of tangent lines to this curve, like all of these slopes I'm drawing here, notice that they're all slopes that are positive. They're all rising to the right. Since they're all positive, that tells you something that relates the derivative here, because the derivative is a formula for finding the slopes of tangent lines. So f increasing apparently means that there are positive tangent slopes. In other words, f prime, the derivative, which is the formula for tangent slopes, is greater than 0. That seems to be a defining property of increasing functions. And now the derivative is in the mix. Let's look over here at a decreasing function. So this is an example here of a decreasing function, f decreasing. And look at the slopes here. All of them, all the tangent slopes that is, are pointing downward to the right. These are decreasing, and so these are all negative slopes. So these are negative tangent slopes. And since the derivative is a formula for tangent slopes, this says the derivative is negative. So, aha! We're learning something about what the derivative can tell you. And just to complete the issue here, I know we talked about when f is constant. When f is constant, that would be where the tangent slope is equal to 0. Because if it's greater than 0, it's increasing. If it's less than 0, it's decreasing. So if it's constant somewhere at a point or a region, the tangent slope will have to be 0. And that, of course, is exactly the derivative. So with this information, we can write down a theorem that will help us solve many of our upcoming problems about analyzing the graphs of functions. Here is the theorem. Let's put it all in one place so we can keep track. If f is continuous, now I've actually limited ourselves to continuous functions because they're nice and most of the functions you see are continuous. There are some issues here if it's not continuous, but we don't need to look at those now. If f is continuous on a closed interval and it's differentiable, which means it just has a derivative, on the open part of that interval, and we just do that because derivatives at the endpoints are one-sided, and that just confuses the issue and makes it a little harder to deal with. So we'll just deal with the open. If we have a function with those properties, then we can use the derivative to tell us about whether the function is increasing or decreasing in various regions. F prime of x greater than 0, the derivative greater than 0, for all x in that open interval, that implies that f is increasing. That's increasing on the entire closed interval. Same thing goes in the opposite direction. If f prime of x is less than 0 for all x in AB, then that implies that f is decreasing on the closed interval AB. And finally, the easiest case of all, if f prime of x is equal to 0 for all x in that open interval AB, then as you might expect, that means f is constant as a horizontal graph on AB. So this is the first of the theorems that will help us use the derivative to learn facts about the graphs of functions. We're not going to prove this right now because we don't have the tools, but later on we'll talk about what would be done to prove this, and that will turn out to be interesting too. But for now, it's important that we look at an example. Here is a typical kind of problem that you will be facing. Find where a function. Now you'll see all sorts of different functions. We'll start with some easy ones, polynomials, but you'll be able to do this for all sorts of functions in the end. F of x equals 3x to the 4th plus 4x cubed minus 12x squared plus 2. Find where that function is increasing or decreasing. Now, if we didn't have the calculus, if we didn't have the derivative here, this could be pretty tedious. This is a 4th degree function, and we'd have to find some way to graph the function and then make some guesses as to where it was going up or down. But with the calculus, we can be completely precise, and the solution is not that hard. So we are going to use f prime, the derivative, to answer our question because of the theorem we just had. So the first thing we'll need to do is calculate the derivative, so let's do that. The derivative f prime of x coming up here is going to be 4 times 3, that's 12x cubed, plus again 4 times 3, which is 12x squared, minus 24x, and the derivative of 2 is constant, so that's just a 0. Here I notice I can factor out a 12x, so I do that. I get x squared plus x minus 2. And then I also notice here that I can factor this So I go ahead and do this. Anything that will make it convenient for me, I will do. X plus 2 times x minus 1 works fine. Now, before I go any further, let us note a couple of things. Note that f prime is equal to 0 only at, well, let's see. F prime of x is the product of three factors. It can only be 0 if any one of those is 0. The first is 0 when x is 0. The second is 0 when x is minus 2. The third is 0 when x is 1. So f prime, the derivative now, can only be 0 at these points. It is otherwise either positive or negative. But we can say even more. Between these numbers, that's the x numbers here, f prime, or you can say maybe above these numbers, but between them I think is probably better, f prime is either, and we'll see this on the next page, always greater than 0 or always less than 0. So if you're between 0 and minus 2, for example, the value of f prime has to be always positive or always negative, but it can't change. Because if it did, there'd be a place in there where the derivative either didn't exist, which doesn't happen here, or is equal to 0, which also doesn't happen because these are the only three places where the derivative is 0. Now watch how this comes into play. Let me rewrite the derivative here so we'll have it handy. The derivative is 12x times x plus 2 times x minus 1. In order to find out where the function's increasing and decreasing, I need to find where this derivative is positive and negative. I already know where it's 0. So let me draw a number line to keep track of my argument. I'm going to mark a minus 2, a 0, and a 1 on here. And that's because those are the three places where the derivative is 0. And notice that I'm not caring about making them correspond to the actual distances on the number line. I'm just listing them in the correct order. And then I'll just make a little division here so I can keep track. Now, if I am below minus 2, the derivative is always positive or always negative. I need to find out which. Well, the easiest thing to do is to pick a number in this region. Now, many students will see minus 2 and then they'll pick something like minus 3. But you should be bold. Pick minus 1,000,000. If you take minus 1,000,000 and put it in this function, what happens? This first expression, this first factor becomes negative. This next factor is also negative. The third one is negative. Negative times negative times negative is negative. That says that the first derivative here is less than 0 in this entire region. Now, if you're bounded between minus 2 and 0, you can't go to 1,000,000. But you can pick an easy number in there like minus 1. If you choose minus 1 and you put it into the function, which is the derivative, remember, you get negative here, positive here, and negative here. Negative, negative, and positive gives you positive. So the derivative is positive in this entire region. Again, I only need to check any point in the region because it's always the same plus or minus sign in this region. Here between 0 and 1, it's a little more awkward. I choose 1/2 as the easiest number I can see. I put that in here. First, it's positive. Here, it's also positive. Here, however, it is negative. 1/2 minus 1 is negative. So that makes the product up there, f prime, is then going to be less than 0, negative. And then above 1, again, I'll be bold and choose 1,000,000. If I put plus 1,000,000 in here, 1,000,000, 1,000,000, and a very large number, these are all going to be positive. So f prime is greater than 0. Now what I like to do here is to draw graphically what that tells me about the picture. If f prime is less than 0, that tells me that the graph of the function is going down as I move from left to right. F prime greater than 0 tells me the function is going up. Less than 0 going down, greater than 0 going up. And that says that f, the original function, is decreasing. Here it's f, the original function, is increasing. Here it's f is decreasing. And here it's f is increasing. So in this diagram, I have answered the question that was posed to us. And I have learned something about the shape of the function, too. Look, the function has to come down, go back up, and come down and go back up again. Now, this doesn't give me a specific graph, but it gives me the right qualitative graph. It tells me about the ups and downs. In fact, I will go ahead and draw here the actual graph of this function for you. Here's the actual graph of this function, drawn freehand, of course. And it's going to be something like this. And it goes down here to minus 30. You can mark a point up here at 20. Goes over here to 3, minus 3, and there's some dimensions for you. Now, this is the actual graph of this function. You can compute this on a graphing calculator or a piece of computer software if you have it. But look at what we have here. Notice that we're going down here, then we're going up here, then we're going down here, and we're going up here. It exactly matches what we learned from this expression above. So this is the power of the calculus here. We will eventually learn to talk about what's happening here at these points where the derivative is 0. Obviously, in this picture, those are very interesting, but that will come up a little bit later. For now, we want to concentrate on the increasing and decreasing, and if you draw yourself a diagram like this, I think you'll be much happier than anything else in finding the way the relationship works. As our next stage, we'll look at functions concave up or concave down. This is where the second derivative is applied. Now this will begin with an observation that'll give us a reason for looking at the second derivative. Observe these two curves. Now they're both increasing. So they are both increasing curves. But they're obviously different. This one bends downward, this one bends upward. It would be nice to be able to distinguish them. Likewise, consider these two curves. They are both going down, decreasing from left to right. But they are different because this one goes up and this one bends downward. So the question that we ask here is, can we distinguish these sorts of things, or these behaviors or properties of the curves? The answer is yes, we can, provided we use the second derivative to do that. And here is why the second derivative is going to be of use. Consider the following. Now I'm going to draw only straight lines. Now watch what happens. I will start with a line of slope like that. Then I'll draw another straight line, and another straight line, and another straight line, and another one. Notice that what I've created what looks like a curve that is curving upward. What has happened here to these lines and their slopes? Well, they're positive slopes. They're all going upward as we go from left to right, no matter which one I drew. And as I go from left to right, this one has a positive slope, but it's rather low number. Whereas when I ended with this one, it's very, very steep, so it's a high positive number, which means the slopes themselves as a sequence of numbers are increasing as I go from left to right. So I have these slopes increasing as I move from left to right. Now, in this picture, watch me do the same sort of thing, except I'll start with negative slopes. And here's another line, and here's another one, and another one, and so on. I'm creating a curve that bends upward as I go to the right. These curves, they're both upward in these cases. Notice that these are all negative slopes. So that's different from these, which are positive slopes. But notice that the same thing is happening to the numbers that are representing the slopes. The slope here is negative, but a very large negative number. And then as you approach this way, the negative numbers are getting smaller and smaller. And you can see we're heading toward what might be the zero slope here. So these negative slopes are also increasing as we move from left to right. So apparently, to describe upward curving curves, we just need to look at the slopes and see that their numerical values are increasing from left to right. That's an important observation. Let's write that down. The tangent slopes here, as we move in that direction from left to right, are increasing. And they're increasing as a set of numbers. This is exactly what characterizes what we'll refer to as concave up. That's what we mean when we say curving upward in these two cases. We'll call that concave up, and we can abbreviate it by just using a curve that looks something like that. Now, as you can tell, what I'm going to do next is say, look at positive slopes. But this time, I'm going to let them decrease as we move from left to right. And I'll do it two different ways. If I start with a slope like this, Now that's a very high positive number slope, and I do more and more of these slopes. You see they are decreasing toward a slope of 0. So they're decreasing from left to right, although they're all positive numbers. If I do it the other direction, and I start with a slope like this, which is negative, and I draw more and more of these slopes like so, I didn't quite get these to cross as much, but you can see I'm creating a curving down curve again. And these are negative slopes because they're all going down from left to right, but they are decreasing as I move in that direction, left to right, because this is a negative number, and as I get further and further in this direction, becomes a larger and larger negative number, farther to the left if you like. So apparently what we have here is we have tangent slopes moving once again from left to right. These are decreasing as a set of numbers. And this is going to characterize these downward bending curves. So this will characterize what we will call concave down. And we usually just abbreviate that with a line that curves downward like that. So with these two, with this vision and the one from the previous page, we can put together a definition that we'll be able to use from now on. Suppose we have a function. Let's let this function f have a derivative on some open interval, and I'll abbreviate interval there, I. And whenever we use I from now on, it'll mean an open interval, so keep that in mind. F, concave up, that's that little symbol like that, concave up on I, means, and this is what we just learned from the pictures on the previous page, means what? It means the slopes are increasing as we go from left to right. Well, what it represents the slope of the tangent to the curve? That's given by the derivative, the first derivative. So that means that f prime, the first derivative, is increasing. That slope value is increasing on I as we move from left to right. And f is concave down, a little picture like that, on I. What does that mean? Well, based on what we saw the other page, that f prime, the formula for slopes of tangent lines, is decreasing on I as we move from left to right. So now we have established that concavity, up or down, is linked to the behavior of the first derivative. Now, if we ask ourselves for just a general function, it happens to be the first derivative here, but it could be any function. We ask a function, we ask the question, how do we know that a function is increasing? Or how do we know that a function is decreasing? Well, the answer is to tell if a function, and in this case, let's just go ahead and say, like f prime, which is a legitimate function here, to tell if a function is increasing or decreasing, we check its first derivative. And that would mean in this case f prime prime, the first derivative of the function we're looking at, which already is a first derivative. In other words, the second derivative of the original function. So now we find where the second derivative comes into play here. And let's go ahead and put this in the form of a theorem. Suppose f, our function, is twice differentiable, so it has both a first and a second derivative on this open interval I. Then we have two situations based on what we've just learned. F double prime of x greater than 0, the second derivative is greater than 0 for all x's in I. That implies that f is concave up on I. So the second derivative being greater than 0 means that the first derivative is increasing because the derivative of the first derivative is positive. Likewise, if the second derivative is less than 0 for all x in I, that's going to imply that f is concave down on I. And so we have a test now which uses the second derivative to tell us where a function is concave up or concave down. Let's try that out on a function. Let's actually work out an example and see what we can learn. This example will be one we've already seen before. We examine this one for increasing and decreasing. So it's 3x to the fourth plus 4x cubed minus 12x squared plus 2. And in this example, we'll look at concavity instead of the increasing and decreasing. So we'll need to get to the second derivative, so we have to pass through the first derivative. The first derivative then is 12x cubed plus 12x squared minus 24x, and the derivative of 2 is 0. This, I won't bother factoring because I'm not interested in examining the first derivative here. I want to go directly to the second derivative. So I will have 36x squared plus 24x minus 24. And out of that, I can factor, it looks like a 12. So I have 3x squared plus 2x minus 2. Now, this expression in here happens to be a quadratic that doesn't factor nicely, so you need the quadratic formula to find where it's 0. So this is 0, 4, and I'll just let you do that. 0, 4, x equal minus 1/3, 1 minus the square root of 7, or x equal minus 1/3 times 1 plus the square root of 7. And for the sake of our graph, which we'll do on the next page, I have approximated both of these to get a sense of where they are. This first one is approximately 0.55, and this second one's approximately minus 1.22. Okay, then let's go ahead and see what we've got here as we go to the next page and draw our diagram. This will be a modified version of the diagram that we created for the increasing and decreasing case. So the second derivative here is 12 times 3x squared plus 2x minus 2. And we know that there are two places where this is 0. The first is this minus 1/3, and we need the one that's furthest to the right, minus 1/3, 1 plus the square root of 7. And remember, we approximated that to be approximately minus 1.22. And then over here we had minus 1/3 times 1 minus the square root of 7, and we approximated that to be about 0.55. So now if I just examine the second derivative in this case, and I ask myself, what is the sign of the second derivative in each one of these regions? It's not hard to figure that out. If I go below minus 1.22, and again be bold, choose a very large number, if I put a minus a million in here, this squared term is going to dominate whatever else is in here. So this is going to force the whole thing to be positive. So the second derivative will be positive in that region. And what does that tell me? That tells me that the original function is concave up, which would look like this. And this is a point to keep in mind. We are using the first and the second derivative in various cases to learn about the original function. It is only the original function that we are really interested in. So by writing this up this way, you keep the test clearly separated from the original function and what you're learning about each of them. If you then check the derivative here between this number and this, and 0 is in between there, put 0 in here, this is going to be negative. So that means f is going to be the original function, will be concave down in that region. And then if you check for a very large number like a million, positive a million, this number up here becomes positive. So the second derivative is positive. And so f is concave up in that region. So we have learned about the concavity of this function based solely on looking at the second derivative here. Now, let me recall the graph that we looked at when we examined this function for increasing and decreasing, and I'll show you that we have the concavity in the right places. The original graph, and I'll draw that freehand here again, was something like this. And it went up to 20, went down to minus 30, over here to 3, and over here to minus 3. And notice that it is concave up here, concave down here, and then again concave up here, which is exactly what we learned above here with the second derivative. So that's a nice verification that this technique is actually going to tell us where a function is concave. Now we'll see where that leads us, because we will be interested in places where the concavity changes from upward to downward and then from downward back to upward. In order to find out where a function is concave up and concave down, it would help to know where a function changes its concavity. And changing concavity actually leads to points which we call inflection points. So the idea here is exactly what I said. You might have a curve that looks something like this, where it changes from concave up to concave down at a point like this. Or maybe it goes the other way. It changes from concave down to concave up at a point. And we'd like to locate these points. Now we have enough information to do that, but we have to be a little careful about setting it up. So here is the definition we will use in this course for inflection points. If, and we'll limit our argument here to continuous functions, which, as I say, are the ones that you most often see in calculus. If f is continuous, so continuity is important here, on an open interval I, so I'll just write open I, and concavity changes, so it changes from up to down or down to up, as we see in these pictures. If it changes at some point on the curve, say x naught f of x naught, then we say the following, and this is just labeling this. We say f has an inflection point at x naught, so at x naught, and what exactly is the inflection point? Well, it is the point with two coordinates, x naught, f of x naught, is that inflection point. So let me draw a picture here. You might imagine that you have your open interval on the x-axis, so this would be I, the open interval. There's some point in here, x naught, and above that point here, the curve is changing its concavity. So right there it's changing its concavity, and that point is the point x naught f of x naught. And that kind of a point will be called an inflection point, and the actual inflection point is the point with the two coordinates, but we say it has an inflection point at x naught. That's the way we phrase this. And the function, of course, is continuous. Now, there's something that often happens here that you have to be careful about. There's an easy assumption to make, and we want to go ahead and clear that up before we go any further. So, recall that we already know from previous work that if the second derivative of x, of f of x, is greater than 0, that implies that the original function f is concave up. That's a picture like that. And we also know that if the second derivative is less than 0, that implies the original function is what we call concave down, which looks something like that. Now, you might, and this is very natural to do, you might then, but this would be wrongly, you might then conclude that the following pseudo-theorem, if you like, holds. X naught f of x naught, a point like this, is an inflection point. So you might conclude that a point is an inflection point if and only if, which is another way of saying equivalent to, so that's another way of saying that, equivalent to the statement that the second derivative at the point x naught is actually equal to 0. Because when it's positive, you have concave up. When it's negative, you have concave down. And so your natural choice is to say, well, when it's 0, that must be where inflection points occur, and only where inflection points occur. Well, it turns out that this is not so. In fact, I can show you that it's wrong in both directions here. And we'll do that by examples, just to keep this very clear. So this example will show that if you have a point, x naught f of x naught, which is an inflection point, that does not imply that the derivative, the second derivative at that point is equal to 0. So that's one direction that turns out not to be true. And here is the picture that generates the idea. Suppose you have a curve that looks something like this. So here's x naught. This is the curve f. And notice it's concave up here and concave down here, but there's a problem at this point. There's no derivative there. There's no first derivative there. So there's certainly no second derivative there, which means it can't be 0 because it doesn't exist. That's our problem. So let me write that out for you. No f prime exists at x naught. So certainly no second derivative, f double prime, at x naught exists. So it's certainly not equal to 0 if it doesn't exist at all. So that means that if you have an inflection point, it might occur without there even being a second derivative around. Secondly, let me show you that the other implication fails. So again, here I'll have inflection point written on the left. But now I will show you that the backwards implication also does not work. Suppose you have the second derivative equal to 0 for some function, where the second derivative actually exists at x naught. Let me show you that that does not imply necessarily that the point in question is an inflection point, and just take the function f of x equals x to the fourth. Now the derivatives are very easy to find here. The first derivative is 4x cubed. The second derivative is 12x squared. And we can say that the second derivative, f double prime of x, is equal to 0 for x naught equals 0. There's only one solution here that makes this 0. But notice that f double prime of x, which is 12x squared, is greater than 0 for x on either side of 0. On either side of our x naught, which is 0. So that means, since the second derivative is greater than 0, it is always concave up. So at x naught, which is 0, there is no change of concavity. No change of concavity. Well, if there's no change of concavity, hence no inflection point. So, an inflection point does not mean that the second derivative is 0, and the second derivative being 0 does not imply an inflection point. There is a connection, but these implications are both wrong. So to summarize this, we can write the moral. The moral is either f double prime at x naught equals 0, or the other case, f double prime at x naught doesn't exist. Those situations give, either one of those gives candidates for inflection points, which at least narrows down the possibilities, but no guarantees. So we can narrow down the possibilities by checking whether the second derivative fails to exist or is 0, and that's good. But you can't guarantee that the points you find are necessarily inflection points. So let's look at an example here. Here is f of x equals x cubed minus 3x squared plus 1. And what we want to do here, and we'll try and do this from now on, find where f does everything that we're looking for so far, where f is increasing or decreasing, concave up or down, and all inflection points. And there will be more things we look for in the future. This is what it means to become skilled at examining graphs using calculus. All right. Well, to do this, we're going to be involved with our second and first derivatives. So those are the tools we'll use to examine this function f. So let's go ahead and compute those tools. So f prime of x is equal to 3x squared minus 6x, and the derivative of 1, of course, is 0. I will factor that right away, so it'll be useful to me. 3x times x minus 2. And I will notice that this is 0 for, let's see, x equals 0 for here, and x equals 2 for this other expression, or other factor. And now the second derivative, and a tip here for you is, When you work on these functions where you're looking for a first derivative and a second derivative, very often the first derivative you will find in this form, and then you'll factor it for later use. But in order to move on to the second derivative, you want to use the first form. It's easier. So if I take the derivative based on this first form, I get 6x minus 6, which is 6 times x minus 1. And this, of course, is going to be 0 for x equal 1. So I have 3 points of interest here, and those will be the points that appear on my graph here. Let's rewrite the derivatives so we have them to hand. 3x times x minus 2 is the first derivative. The second derivative is 6 times x minus 1. And then in here, let's go ahead and mark the points of interest. There are 3 of them, 0, 1, and 2. And let's see, for the first derivative, 0 and 2 are the numbers that make this go to 0. So those are the ones that will be of most interest for the first derivative. And then for the second derivative, here, only 1 is of concern. So I'll mark this like so. So up here in this horizontal region, we'll talk about the first derivative. So I want to know what the sign, the plus or minus sign of the first derivative is in each one of these 3 strips. Well, if I'm below 0, I have a negative number here, and this is negative, so negative times negative gives me a positive number. That tells me the original function is increasing, and I draw it with a line like that to remind myself. In this region between 0 and 2, I'll take an easy number like 1, put 1 here, it's positive, 1 here, it's negative, so this becomes negative. So the first derivative is negative here. That tells me that the original function is decreasing, which I'll mark like this. And then if I go to a very large number, something beyond 2, this is clearly positive. So that tells me that the function is increasing. And so now I know where it's increasing and decreasing everywhere. Let us now examine the concavity issue. That is determined by the second derivative, which has a breakpoint here at 1. So that's why we have just 2 strips here. So we'll look at the second derivative and ask ourselves, if we're below 1, pick a number, easy number like 0. This becomes negative. So that tells me the original function is concave down. And then over in this region, if we are above 1, this is certainly positive. So that tells me the original function is concave up. So it looks something like this. So now with this diagram, notice this diagram has everything we need and gives us a hint as to what the curve actually looks like. That's the advantage of doing things in this way. Finally, let's look at the graph here. So the function is x cubed minus 3x squared plus 1, of course. That's the original function that we've always been interested in. Here is what the graph looks like. Something like this. Here is 0. And here, where the concavity is changing, is 1. And here is another point, 2. And look at what we have here. The curve is going up here. It is going down in this region, and then it is going up again. That exactly mirrors what we had on the other page. Notice, too, that it's concave down in this region and then concave up in this region, which, again, reflects what we saw on the previous page. So the graph is really determined by the information we got on the previous page. That's helpful to know. This is how calculus can allow you to graph functions that you may have no sense of. Let us look at another example that's different from a polynomial. Let's take f of x equals x times e to the minus x, say. And let us find the same thing. Find the same information as we did above, which is to say where the function's increasing or decreasing, concave up or down, and where it has inflection points. So a solution, we begin again by writing down our tools, and our tools are the first and second derivative. So the first derivative of the function in question, which is x e to the minus x, that's a product. So we'll leave the first element x alone times the derivative of e to the minus x, which is minus 1 e to the minus x, plus the second one e to the minus x left alone times the derivative of x, which is just 1. That factors nicely. Let's see, e to the minus x comes out, and we have then a 1 minus x left over. This we will just note as we pass. This is 0 only for x equal to 1. We'll also notice that e to the minus x is always positive. Anything with a base of e or any of the numbers that are allowed to be bases, an exponential function like this will always be positive. So that's good to know. That was the first derivative. Let's compute the second derivative, another tool we'll need. And let's see, I'll just work from this second form. I will leave e to the minus x alone times the derivative of 1 minus x, which is a minus 1, plus the 1 minus x times the derivative of e to the minus x, which we've already done, which is minus e to the minus x. From all of that, I can factor out an e to the minus x, certainly. And what's left here? I'm going to get a plus x. I'm going to get a minus 1 and a minus 1, so it's x minus 2. This is 0 for, let's see, x equal 2. So now I have the information I need to draw my sketch here, which will allow me to analyze this function. 1 and 2 are the only 2 points. 1 and 2 are the only 2 points here of interest. So let's see, the 1 is of interest for the first derivative, so I can write like that, and the 2 is interest for the second derivative. So up here I just have 2 strips for my first derivative. So let's find out what the first derivative is doing in the first strip. If I'm below 1, I come up here and put a very large number below 1, or pick an easy number like 0, for example. Put 0 in here, I get a positive number. So the first derivative is positive. That tells me the function f is increasing, and that's an arrow going upwards. Then if I go to the right of 1, choose a million if you like, this number becomes very negative. So f prime is negative here, which tells me that the original function is decreasing and hence goes downward. In these 2 strips down here, we're interested in what the second derivative is doing. So let's see, to the left of 2, I can pick an easy number like 0. Put it in here, this becomes negative. So that tells me that f is concave down and looks something like that. And then over to the right, if I'm above 2, go to a million. This is positive. Then f is concave up, which looks something like this. So now again with this diagram, I have an idea of what this curve ought to look like. It ought to go up and down and be concave down here and concave up here. Let's see if that's the case. If we take the function f of x equals x times e to the minus x, and we produce a graph of it, and you can do this with a graphing calculator or by hand, here's what you get. You get something that looks like this, where this peak here is occurring at 1, and this point here where there's a change of concavity occurs at 2. And again, see that the curve is rising on that side and decreasing on this side. And then there is a change of concavity. It's concave down up to 2, and then concave up for the rest of the time to infinity. So that was all reflected in the graph on the previous page. That's the power of the calculus here. Now, as a final note, we can remark on another interpretation of inflection points. And this is sometimes useful when you're talking about rates of change. Inflection points of some curves, say y equals f of x, can be interpreted as follows. We can say that the rate of change of y with respect to x. Now, of course, we could write that in symbolism. We could just write dy dx if we wanted. But we want to emphasize rate of change here. The rate of change of y with respect to x changes from increasing to decreasing, or from decreasing to increasing. That is what an inflection point represents in terms of the words rate of change. The rate of change is increasing on one side and decreasing on the other, or the vice versa, decreasing on one side and increasing on the other. So there's another interpretation of inflection points in addition to what they tell us about the graphs of curves. One last note as a look ahead, we will look at what are called logistic growth curves and just give them a brief look. Logistic growth curves are curves that represent growths of population, so the growth of a population. But rather than just the growth of a population with no restrictions, real populations are limited by food and space and so on. So that what would the graph of a population with those kinds of limits actually look like? So the growth of a population when space, say, or food are limited. Well, here's the kind of graph that you end up getting. First of all, you start with a non-zero starting population. That makes sense. You can't get a population if you don't have one to start with. So a non-zero starting population. And then for a while, the curve will grow exponentially. So the initial growth of such a population, as is always the case, the initial growth is exponential. Then the limitations kick in. The lack of space or lack of food. And what happens is that the curve actually starts approaching a theoretical maximum here. It begins to go asymptotically to a line, say, at height L. So this is an eventual decline of the growth. So the growth does not continue exponentially forever. It is in fact limited by the limitations of the resources. Now this L is actually sometimes called, let's bring that down here, L is sometimes called the carrying capacity of the environment. And that will differ from environment to environment. Now what do these curves actually look like? Well, the form of these curves, and you'll study them later when you look at differential equations, although there are some nice examples at this point in the course. The curves have this form. They're y equals L, and that's that carrying capacity constant, over 1 plus some other constant, times e to the minus times a constant times t, where t is time. This graph will have a shape that is representative of populations that operate under limitations. We will examine this later. You can play with this now. You can look at its first and second derivative and so on. It takes a bit of algebra and manipulation, but you'll learn much more about this if you study differential equations or if you're studying population biology and such. Time for some exercises. The first one, I will give you a function the likes of which we haven't looked at before. Instead of a polynomial or something involving the exponentials, we'll go ahead and write down a rational function here. X squared plus 2, x over x squared plus 2. And what we want to do here is find everything, so go ahead and let me write this all down for you. Where f is, what do we want? We want increasing, decreasing, concave up, concave down. We want to find inflection points. Later we'll do other things. In fact, here, since it's a rational function, let's toss in asymptotes, because those will be part of the graph. And finally, we want to produce a graph of this function. So that is your task. It'll take a while, but did you find this a challenge? Let's see what we need to do. Here is our original function again. X over x squared plus 2. And let me just observe right now that this denominator here is always positive. That means, in particular, it can never be 0, which means you will never have any vertical asymptotes for this rational function. So that's going to make life easier in many places. Now, as usual, we'll need our tools. We'll need the first derivative and the second derivative. So let's compute those. The first derivative, well, that's a quotient, so there's no way around it. We'll have to use the quotient rule. So let's go ahead and write down, I always like to start with the bottom, x squared plus 2 quantity squared. Then I start out the top with the bottom, which is x squared plus 2, times the derivative of the top, which is 1, minus the top, which is x, times the derivative of the bottom, which is 2x. Now that pretty nicely simplifies. The bottom is still x squared plus 2 squared. The top is x squared minus 2x squared, and we have a 2 here. So this will be 2 minus x squared. Now that's not so bad. We might note here that a rational number, of course, can only be 0 where the top is 0, and the bottom, as we already know, is positive. So this will be 0 for what values of x? Well, whatever makes the top 0, and of course that means x equals square root of 2 or minus square root of 2. Okay, that takes care of the first derivative. Let us now look at the second derivative. And we'll work with this final expression, which is, again, one of the values of simplification. This is a lot easier to work with than this first version. We'll work with this, and we'll have to use the quotient rule again. So in this case, we'll need a little more space, perhaps. We'll have x squared plus 2. It's squared here. We need to square it again for the quotient rule. So it's to the 4th power. Then we start off with x squared plus 2 squared times the derivative of the top here, which is minus 2x, minus, now the top untouched, 2 minus x squared times the derivative of the bottom. And that will be 2 x squared plus 2 to the 1 power times the derivative of the inside using the chain rule, 2x. So there is our long expression. We'll do some algebra now to clean this up. You may notice there's a factor of x squared plus 2 here and another factor of it here. The two of those, we can factor one out and then cancel with the bottom. And we can also pull out, let's see, we can pull out 2x from both of these. So if I do that, I have 2x, and here's what's left in the inside, minus x squared plus 2, minus 2 times 2 minus x squared on the top. And on the bottom, we have dropped this by 1 power due to the cancellation. So this is now x squared plus 2 cubed at the bottom. And finally, inside here, we can clean this up, multiply it out, and add things together. And we'll get 2x times x squared minus 6 all over x squared plus 2 cubed, of course. And this expression is going to be 0 for what? For x equal, well, x could be 0 for 0. And what would make this 0 up here? Well, when x is equal to the square root of 6 or the negative of the square root of 6. So there are the two numbers. And let's go ahead and use these two tools to examine the graph of the function in the way we've been doing previously. So let me rewrite these up here. F prime of x is 2 minus x squared over x squared plus 2 quantity squared. And the second derivative is, from the other page, 2x, x squared minus 6 over x squared plus 2 cubed. Now, we're going to draw a chart like we've been doing, and we'll put on here all the numbers of interest. Now, that would be, from left to right, minus square root of 6, minus square root of 2, put the 0 here, and then square root of 2 and square root of 6. Taking no account of their actual positions on the number line, all that matters here is their order. Then, for the first derivative, it was the 2 square roots of 2 that affected the first derivative. So let me go ahead and just indicate those. And then it was the 3 numbers, 0 and the 2 square roots of 6, that affected the second derivative. So I'll bring those down here so I know where to mark them. All right. On this horizontal region, we're talking about the first derivative's effect on the curve. So I want to know what the first derivative's plus or minus sign is in this region. If I go below minus square root of 2 to minus a million, say, when I get up here and I square it, it becomes 2 minus a million squared. So this is definitely negative. In fact, whether it's minus a million or plus a million, we're going to get a negative number here, which tells me that the derivative is less than 0 here, and also on the other end, it is less than 0. Both of them tell me that the original function is decreasing on those regions, and therefore going down. In the central region, the easiest number, of course, is 0. I put 0 here, I get a positive number. That tells me the first derivative is positive, the function is increasing, and therefore going up. Now for the second derivative, I need to look to the left and to the right of square root of 6, and because of the x squared here, if I choose a very big number in either direction, when it is squared, it's going to make this positive. So that means that with this x out front to give me a negative because I'm over here, I will have f prime less than 0. So I will have a negative number times a very large positive number. And this would give me f concave down, which means it looks like this. On the other end, I have f double prime. Again, this is a very big positive number, but this is now positive. So the second derivative is positive here. And this is f concave up, which means it looks like this. Now, in these two regions in here, I am looking for numbers that are between minus or plus square root of 6 and 0. And It's easy to pick numbers like that. For example, between 0 and square root of 6, we might choose 1. Putting a 1 in here gives me a negative number. So this makes the second derivative negative here. And if I put a minus 1 in here, this will be negative times negative, so this would be positive here. And so this second derivative greater than 0 tells me that concave up is what the original function is doing. Second derivative less than 0 tells me the original function is concave down. So it looks like that. And because at each one of these three division points the concavity is changing and the derivative is defined throughout, that means all of them are inflection points. So I have found all the information I need again from this chart. Let's see what it tells us about the graph. The graph, and here's the function to remember it, is x over x squared plus 2. That was the original function. Now, one more thing. Well, we did mention asymptotes when we talked about this function originally. So let's observe that no matter which way you go, if you take the limit as x approaches plus or minus infinity of x over x squared plus 2, you always get 0 because the denominator has a higher power than the numerator. And so this limit will always be 0. And that therefore gives you a horizontal asymptote, which is y equals 0, the x-axis. And one other thing you can notice, just as a nice observation, that if you compute f of minus x, you get minus x over x squared plus 2, which is the same thing as computing minus f of x, which says that this function is symmetric with respect to the origin. Or if you like, it says that this is an odd function. Now, these two pieces of information will assist us in looking at the picture. So, in the end, here's the kind of picture we get. Something like this. So it's symmetric with respect to the origin, so it looks the same on both sides, although one side's flipped over. Let's see here. Where the concavity changes here, which is an inflection point, is minus square root of 6. Here is a point where it was decreasing down to this point, and now it's increasing. So this is minus square root of 2. This point in the center is 0, again an inflection point, concave up to concave down. Here's a point where we're changing again from increasing to decreasing, that's square root of 2. And then another point of concavity is at square root of 6 here. And this is where the concavity is down and then changes to concave up. Notice that the function is going down here, up in this region, and then down again. That it is concave down to here, concave up, concave down, and concave up. All of this was reflected in the previous chart. So you can see how much you can learn about a function from doing the charts. All right. Let's look at another kind of problem. And this is, in a sense, the reverse of the last one. In the last one, you had a function, and you were asked to find the graph. In this one, I'm going to give you a bunch of properties of a graph and ask you to draw me a picture associated with that. So graph a single function, which is unknown, but we'll give it a name. We'll call it g of x, with all these properties. And there are many functions that have all of these properties, but come up with one that's relatively simple. So the function is defined, and it has a derivative. So it's defined with a derivative everywhere. And everywhere means all real numbers. So no matter where you look, there's a value of this function. Then let's say g of 0 should be 2. The derivative at 0 should be minus 2. G of 4 will be 3. The derivative, first derivative, at 4 will be 3 also. Let us say that the second derivative is greater than 0 for values of x greater than 4, less than 4. And let's take the second derivative to be less than 0 for values of x greater than 4. So these were less than 4 here. These are greater than 4. And finally, let's go ahead and give a limit. The limit of g of x as x goes to positive infinity only is equal to a height of 4. So with all of these properties, try to produce a picture that represents g of x. Had all those properties we looked at. Now let's see if we can come up with a picture that represents them all. One of the properties was that the function is defined everywhere, so we know we'll have a graph everywhere. We know that g of 0 is 2, so that tells me that up here at a height of 2 there's a point of the function. The derivative at 0 was equal to minus 2, so I don't know what the curve looks like, but I do know the slope is slanted downwards, something like that. Then I was given the information that at 4 the derivative, or the value of the function is 3. So I have a point up here at x coordinate 4, y coordinate 3. And I was told that the derivative at this point is 3. So that gives me a slope that's slanted upwards, something like that. Now I know that the function has second derivative greater than 0 for all the numbers that are less than 4. So in the region less than 4, I want concave up. And then to the right, I found out, I was given the information that it should be concave down. Finally, I was told that as I go far to the right, the limit of the function should be 4. So if I mark 4 up here, then I want this function to approach 4. So with this information, it looks like I can come up with a picture. Maybe something like this, curving up like this and then coming out to 4. This is concave up until this point above 4, then concave down, so that matches, and everything else matches too. That is as simple as it gets. But you have to know what all the different properties mean in order to come up with a drawing like this.